All right, the next one we have is a t-shirt, Hide Your Books, the Bibliomaniac has arrived, and Shmoo Group mousepad. So the trivia question for this is, in trigonometry, what does the acronym SOHCAHTOA stand for?
Sine over cosine, opposite over adjacent. Yeah, and what is it over
Well, not quite. There's a few of the words were... All right, with the hand up in the air.
Sine is equal to opposite over the hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent.
All right, very good, sure. Come have a t-shirt and a mouse pad. I guess you don't need the book that we just gave away. All right, before we get started, a few small announcements in addition to the stuff Bruce just talked about. We have no more wristbands for the party tonight. If you are not going, feel free to find somebody that is going. There are still a bunch of people that want to go, but we just don't have enough wristbands to let everybody in. So if you're not going, find somebody. There's a lot of people that want them. If you are interested in buying any of our swag from past years, feel free, head up to the registration desk. We have some free stickers to give away, as well as some of the past bags. But for now, how to be an RSol?
RSol, yeah.
An effective bug hunting in Solaris. And so please give a warm welcome to Matt Hillman.
Okay. Can everybody hear me, first of all? Yes? I'll take that as a yes. I can't hear anyone saying no. Okay, so I've been working on owning Solaris. But then I got a bit distracted, and my work took me in a direction that I wasn't originally intending. So my name is Matt Hillman, and I work for MWR Info Security in the UK. And you can find all of the research that we do, including what I'm talking about today, at the lab's website, the URL you see on the screen. I'm also a member of NMRC, and I think I'm contractually obliged by my membership in this group to have Gas Mask Girl in my presentations at least once. So there she is. Okay, so I'm going to start off talking about how I got to where I am. As I said, I kind of went in a different direction to what I was originally intending, and I think it's important to understand why I was doing what I was doing and why I implemented it in the way that I did. I'll then talk about what RSol is and how it operates, and then show you some demos. And I should say the demos are not going to be quite as I had originally intended. I had intended to get a Spark machine with Solaris running here that I would be able to show you it running on, and unfortunately that did not pan out. Don't buy from eBay. But yeah, and then I'll talk about where I'm going to go with this in the future, because I've got quite a lot of stuff that I want to do in the future with this as well. So, how I got here. I wanted to look at Solaris security. I wanted to start finding bugs, fuzzing, and so on. And I realized that there wasn't really the tool chain, at least publicly, on Solaris that there is on other popular platforms in order to do this. So I started initially very quickly looking at Sully and thinking, let's just get something going really quickly and see what we can find, and realizing that, well, there's not a process monitor for Solaris that you can use in order to get good information about what's happening with your fuzz cases. So I looked, and I should say as well, I hadn't done anything with Solaris before, so this was also me learning Solaris at the same time. So I started looking at the options that I had that I could use to enhance this rather than just waiting for it to die and seeing what had happened. Obviously, I could use core files, kind of simplistic. I could mimic what the process monitor does in Sully and Windows, which is basically it acts as a debugger, attaches to the program that you're fuzzing, and attempts to glean information about what's happening. And to do that, you would use on Solaris the proc file system, which is how you attach as a debugger in Solaris. And then there was dtrace. Dtrace, this was a new thing to me. I'd seen some talks about it before. And dtrace is quite interesting. For those that don't know, dtrace is a dynamic tracing framework available in Solaris, and it's available on some other platforms as well now. And it's very different to attaching as a debugger. You basically lay probes within the system at different levels. and it's implemented as a kernel feature, so it operates quite differently. The goodness that you get from dtrace, there's been a lot of work done before. ReTrace has been presented several times before that makes use of dtrace to aid you in reverse engineering or whatever you're doing. And you can trace at a wide range of levels. So you can trace at the source level, you can trace at the protocol level, you can trace at the instruction level, and you can do all of these things at the same time, which is obviously very useful. I've said hit probes are queued, so when you're placing a probe and you hit that probe, it's actually placed in a queue which dtrace will then check at sort of comfortable intervals. And this kind of gives you the performance increase when you're actually running the process, rather than a breakpoint that you might set in a debugger, where the process actually has to physically stop while the debugger does its thing. These are queued, and then dtrace will check them and run the actions. So you get some performance increase there. And you can have highly specific conditions on your probe, so you can say you want the program counter to be equal to this value at this particular point in the program or something. And this has been used in ReTrace in the work that they did to kind of monitor for stack overflows and monitor for heap overflows and do quite specific things that you wouldn't be able to do simplistically with a normal debugger. But there are some issues with using dtrace in this way as well. It's designed to be very production safe, which sounds like a good thing, and usually it is. But if you're using it for fuzzing or reverse engineering, not necessarily. Largely down to probe skips, which you can guard against by increasing the queue size and increasing how often it checks the queue. But if you do that, you sometimes lose the performance increase that you get from having them queued in the first place. And it's really designed for system administrators to be able to use this on a production system to troubleshoot and find things that are wrong with the... We're not being picked up. Okay, cool. So yeah, on a production system without interfering with the production system too much. It's also been found by people that have done more work with dtrace than me that it's harder to create a generic solution that will work for all programs that you can just throw at it and off you go. You're going to be placing a lot of probes, which can sometimes be a problem for probe skips and so on. So you very often have to tailor what you're doing to the specific process that you're investigating. And I really wanted to get something that was more generic, that you could just quickly get up and running, and then possibly use dtrace later on or in addition to look for other specific things or to investigate the process further in a quicker or more efficient way. And of course, we can do most of this stuff anyway, and a lot of people are doing it anyway without dtrace on platforms that dtrace isn't available. So I really got to wondering whether dtrace, was really the answer, and when we should use dtrace and when we shouldn't. And I'm not totally there with implementing dtrace in RSol. It basically is at the moment a debugger. But I can demonstrate from this that I've implemented the things that were being implemented with dtrace. You can implement them in this way as well. But as I say, I got to this point because I was originally just trying to get a process monitor for Sully, and then just realizing that, well, actually, I can do a lot more with this, and it's actually a really useful component to have. So what I want this to grow into is a suite that uses dtrace and debugging techniques interchangeably, so that you can experiment with them and use the appropriate method where you can. So what it is a library written in Ruby. And I emphasize it's a library because it's not a finished tool on its own that you can just go and run and it will do magical things. You can use it to implement tools that will do things like code coverage and process monitoring, etc. So this is a bit of an overview of the architecture. I'm not going to go into too much detail. You've got the core class RSol, which is what most people are going to use to make the key calls to do stuff. procfs is an important class. That's the interface to the proc file system. There's a few native extensions as well to get around some limitations of doing it in Ruby as opposed to a native compiled language. And this is a bit of an overview of the API, just to give you an idea. There's more stuff in there as well, but it just gives you a flavor of the kind of things that you can do with it. And you can see it's basically all the usual debugger stuff that you would expect to be able to do. There's also a lot of data that is stored within an RSol instance when you create it and attached to a process. And it's structured basically around the way procfs structures it. And the example there, you've got the process status information, so the overall process state. You've then got within that lightweight process state, so these are like kind of threads within the process, registers associated with those threads, and then at the end I've got a specific register, the program counter. So there's lots of data hidden in there as well that you can extract and make use of. And that's just a really quick example to show how you would make use of it. Now, here's where I would be doing my special magical live demos, which I'm not able to do because my Spark machine is broken. So it's going to be screenshots, unfortunately, which is not amazing. But it's a console, so it's largely the same thing. So most of these are going to be in IRB, just to show you the kind of stuff that you can do originally in an interactive fashion. Obviously, it's not now. So there I'm just including the library and creating an instance. And then you can attach to a process by PID or name. If there's more than one process with the same name, it's going to give you this little prompt. And once you've selected it, you can see the PID field telling you which process you are actually attached to. And this is an example of the process information that you can get from it. If you simply print the instance, you get a toString method that descends into all of these variables and fields and prints them out. It's a bit hard to read in such large font, but you get the idea. It's going to scroll quite a long way. That's the lightweight process information. You get a lot more specific information there. Registers, a stack trace, including all the register windows. And this is just a very quick example, again, of using basic calls to set breakpoints, stop the process. It can disassemble stuff. You can usually pass it symbols as well as memory addresses in each instance. And yeah, you can also disassemble whole functions at once, and I've passed it there a prefix of address, starting with $, so you can do nice formatting and be able to read stuff quite easily. Okay, so a bit more of a practical example. This is going to basically be how you would implement a process monitor within Sully or within whatever else you're using. I'm just spawning the process here. It's going to spawn the process and just be stopped on the entry point, so you can pass it any values you need or manipulate it however you want before you actually run it. And here I'm creating a fault set. So you can monitor for different faults, different types of faults, and you can monitor for several of those at once. I'm just using one here, but you create this fault set object, which you can then pass in as like a bundle of faults that you want it to trace. So here I'm using the bounds fault, and all these things are stored in constants. So you've got the procfs constant class there with obviously the fault bounds. And then you pass in the object and you say, right, I'm going to trace these faults in this process. And if you were now to print which I wish I could do, but I can't. If you were now to print the lightweight process information, you will actually see that it will say traced faults and it will say FLT bounds. And obviously in a normal situation, you'd be passing it in pretty much all of the faults if you're fuzzing, so that you can get a view of all of them. Okay, and then we continue the program, so we're now running the program. And it wants us to give a bit of data, but not too much. Give it a bit more. So there's quite a bit of data in there. And then what I'm calling here is wait for event. One thing that I want to do in the future with this is rework it a little bit so it's a bit of a cleaner interface to be event-driven. But for the moment, you call wait for event, and you can pass it a timeout and things like this as well. This is returned true, which means that an event of interest has occurred and the process is stopped and waiting for you to take some action or print some information. So then I'll print the instance out, and we can see PR stopped, so the process is stopped. and the iStop flag showing that it's stopped on an event of interest. Obviously lots of other information you might want to get from this as well. Then you can see why stopped. So here we're getting information about actually why it stopped. It's faulted. It could be also that you've requested it to stop, or it's stopped on a signal if you're tracing signals or system calls. In this case, it's stopped on a fault, and it's telling you that it's stopped on a bounds fault. You then get a little bit more information about it. Basically, this fault will also generate a signal in the normal run, which will be delivered to the process if you were to continue it at this point. It's obviously a seg fault. The map error gives you a bit of information about why it's a seg fault. In this case, it's an address that doesn't make sense, isn't mapped to anything. You can also get, if you're writing to a region that isn't writable or something like that, you'll get a different flag there. And then the registers, and you can see a lot of 0x61, which is your A's in hex, obviously overflowing things we shouldn't be there. And the return address, very nicely, all A's. So that would be quite a fair indication that you've got some exploitable condition there. Interestingly, in Spark, stacks are not always exploitable in the normal way. You have to have some level of recursion for that to work, but that's beside the point. And this is just an example. I've implemented it within Sully as well, so I've written some wrapper scripts that make it. Obviously, Sully's written in Python, and I've written it in Ruby, but with some wrapper scripts, you can get that to work. I was actually going to show that. I obviously can't. But this is, once you've caught a crash, you can then explore the crash bins in the normal way afterwards. This is a Solaris-specific crash bin, and it's just giving you a summary of the crash that it's found there, and some key registers and values that are useful in deciding whether or not this is an interesting crash to you, with the return address and stack pointer and so on being overwritten in a way that might be quite interesting. That crash obviously seems quite interesting to us. So this is another demo here. This is a demo program that I wrote that it's just basically going to give a different message to root to everybody else. So just to show you the normal run of that program, your UID is 100, go away. And this is a system call proxy, which I've implemented with RSol. So a common sort of thing that you can do with other tools, but just as an example. And this is one of the things that in a previous delivery of this talk, I've actually shown writing the majority of this tool, and it's sort of 100 lines, and most of that is making it look pretty when it outputs things. I can't obviously do that now, but I can show you it in operation. So what this does is it traces all of the system calls and intercepts them and lets you take some different actions on them. So this is the get UID call, and you can block it completely, or you can ignore it and let it go through. So we're going to let it go through, and then this is the system call returning, and it's returning our UID, and it gives you the opportunity to modify that return value, which we will. And we're going to change that to 0, so we're going to look like we're root. And then there's going to be some other system calls that we're not really interested in, we'll skip over. And there, now our UID is root, and the program thinks that we're root. Obviously, that's not going to be a security mechanism I hope anybody would use in real life, but it's just a nice little example of how you can intercept system calls. A more practical use of this would be for things like fault injection. So you would intercept system calls, maybe open calls, malloc, and so on, that you want to, well, not malloc, but that you want to force to return strange values, or you want to force them to return an error state, so that you're running branches of code that you wouldn't necessarily run just from running fuzz cases. It's sort of almost luck if you're going to get a system call that returns an error or not, depending on what resource usage is on the system and so on. So you can do that to basically fuzz more of the code, and that would be a good way of doing it. Also, things like run tracing and code coverage can be done with this. I've implemented a very simple example of that. This uses, I should actually explain before I show this. This uses the Spark instruction type class that you saw in the infrastructure diagram, which is able to search through memory and categorize different instructions that it finds in memory in more specific or less specific ways. And what, in the case of this, it's looking for is flow-altering instructions. So any instruction that can alter the program flow, any decision points in the program, basically. So it searches through and finds all of those and basically places breakpoints at there and records when they're hit and where they redirect you to. So you're getting a trace of all the decision points that are relevant in the program. It's kind of an easy way to identify the basic blocks in the program. It's not completely foolproof, because if strange things are going on in the assembler, it's going to fall down. Another way that you could do this that's been implemented on other platforms is to pass it into IDA and get out, retrieve the blocks from IDA and pass that into the program and so on. But this is just a simple way of doing it. This program here, I'm just saying I want to run a block trace. So you can do it at the function level or the basic block level. In this case, it's the block level. I'm logging it to b.txt, and then demo trace is the program I'm running. This will be doing it on the function level. So the difference between the block and the function level is simply, instead of looking for flow-altering instructions, I'm looking for a more specific kind of flow-altering instruction, which in this case is just an entering instruction, which is basically a call instruction or anything that's going to go into a function or subroutine. And at the moment, it just outputs very basically an ugly trace of when decision points are hit and where they get redirected to. That's the block level one, and that's the function level one. And you can just see it's different. I'm not going to go into detail about why it's different, but obviously it's a different kind of trace. And obviously this is quite a primitive trace. You could store this in a better way and do better things with it, but just from a simple perspective, you can parse this into an actual visual graph, which I've done here. So this is the block level trace, or a portion of it, and that's the function level trace. Obviously, you can see the function level trace, a lot less going on because you're just looking at what's calling what as opposed to every single decision point. And you can do some nice stuff with this, which has been done with PyMay. I don't know if I'm pronouncing that correctly, and PStalker. And that's kind of my inspiration for doing this, really, in that you could run a run trace of a program running all the functionality you're not interested in, and then run another trace with a bit of functionality that you think might have a bug in it or that you're interested in looking at, and use basically your run trace to exclude all of the code in the second run trace that's not related to that function, that's related to normal operations, GUIs, or input, output, whatever. And it lets you zero in on the code that you're interested in. And obviously you can also do code coverage with it, because you're able to determine which sections of code have executed and therefore which haven't. At the moment, that's just a simple proof of concept. Obviously, you can use it to code a much more, put a nice GUI on it and make it a lot better, but it just shows the capability. This is going a lot quicker because I'm not doing it live. This is another little feature I've implemented, which allows you to cause malloc to run inside the process. So instead of, if you want to do stuff in the debugger, you want to actually inject code into the process, you're going to want somewhere to put that code, and this is a simple way of doing it. So what I've spawned my demo process, and I've called malloc, and I've just malloced 100 bytes within the process, and it's given me the memory address where it's malloced it. And the address format call just formats it in a nice way so we can see where it is. This can be used. I've actually got a partially working, I was hoping I was going to get it completely working when I was here, implementation that uses this to do automated inline hooking. So it will take a function call, overwrite some instructions, put in a handler so you can redirect stuff from that function call. That again can be used for fault injection, for things other than system calls, for actually calls within the process, or for doing any other strange evil things that you want to do in the process. If you actually want it to run in the process memory space rather than stop it in the debugger and have the debugger do it artificially. Oh yeah, and I'm just writing a NOP instruction into the memory I've allocated and disassembling it just to show that works. A bit of a summary of the advantages. I've kind of covered this already. In dtrace, it's good for specific solutions. It's very fast, but it can lose information. Oops. And the debugger can be a bit slower, but you get no information loss, and it's easier to implement these more generic solutions. So what my goal is to combine both of these approaches in one tool suite. REtrace has already done some work in using dtrace to do this, but development seems to have kind of stopped on that. I'm not sure if they're still working on it or not, but I'm going to try and integrate it into RSol in my own way. And then one example, the REtrace guys have got a nice set of scripts that monitor processes for stack overflows and heap overflows specifically. So rather than waiting for it to crash, you're actually proactively looking at things. And that's an example of something that you could put into a program that you're fuzzing and still have all the normal debug monitoring and so on, and have something like that on top. So that's just a simple example of how you may go about doing that. So future work, obviously I want to implement more dtrace stuff, which I was hoping to get more done before I got here, but it didn't pan out that way. And that's going to lead hopefully to metrics and better comparisons between the two, where I can actually say, okay, I've run 1,000 fuzz tests using these different methods. Which one's quicker? Which one gave you the most information, the most useful information, and so on. And actually to get some more polished working tools. The examples I've given a sort of proof of concept, really. I want to get them into a more usable state so that you can quickly get up and use them. And actually then start using it to look at Solaris security, which was my original goal before I got slightly distracted and started writing crazy tools. Few greets and props. Reached them a little quicker than I was intending. VulnDev, who basically provided me with a bunch of Spark servers to actually do this. Squidly for attempting to get a Solaris machine working for me here. She, obviously we didn't succeed with that, but she did stay up very late, so I've got to thank her very much for attempting to. LEH, you know who you are and why. And Shutzi, putting up with me. Questions and schmooballs. Yes.
Yeah, are you familiar with also systrace on OpenBSD, NetBSD, and the successes and failures of in relation to your work?
Yes, systrace. I have read about systrace. I don't know a great deal about it, but if you have, information you think is pertinent, I'd certainly like to hear it. So, yeah. Anybody else? Yes.
Regarding, I guess, some of the stuff with retrace that's been done and kind of what you're incorporating, one of the biggest issues I've seen is with dtrace, the inability to do like for loops and stuff when you have large data structures, and when you want to keep those data structures in the Ruby side, that's the timing is actually affecting the process that's running. It's a large program.
Yes.
Tons of dynamic memory. I mean, I've seen, I've had real big problems trying to incorporate that all together. And I was wondering if you had any thoughts of a way that may mesh together well.
Yeah.
Because I didn't see a great way of doing it within dtrace, which frustrated me. And then, being able to do it in Ruby was great, but then if it was too slow, and the process wasn't really, I wasn't trying to debug it. I was trying to do it all in real time, essentially.
Yes, yes. I think that, to be honest, part of the way I've approached this is actually that maybe we don't care so much if the process is running slower when we're fuzzing. Obviously, to some extent we do, because we don't want to sit there all day while we're waiting for it. In terms of how you would fix that in dtrace specifically, I'm not really sure. I would hope that you would be able, as you say, to keep the data structures that you want in the Ruby side, but then you're facing the same problem of, if the process is waiting for you to do something, it's going to slow it down. So I don't have a clear answer for that at the moment, I'm afraid.
That was just something that I've run into. That
Yeah.
if you somehow could eventually when it gets to that point.
Yeah. This is the kind of thing that I'm definitely interested in. So, and if anybody else is interested in the same issues and wants to kind of get involved, then I'm definitely interested, and grab a business card from me after or something. So yeah. Yes.
Have you heard of the Monasonic tool, which is like Ruby wrapping, Ruby mining interface, and Windows debugging? Called Ragweed?
It seems familiar to me, but I couldn't say offhand. But it's tools like that which I'm trying to kind of mimic for Solaris. So PyDebug and so on. Solaris is procfs for debugging, so it's not quite the same. But the same principles apply in that the bindings are, you get the bindings and then you can do it within Ruby, but it's not actually ptrace. So, no more questions? No? Okay, well, thank you very much.
Systrace.
Ah.
He's got a question. So I was just like, wow, Slashdot's got a thing. So if you Google for Systrace,
Okay.
Robert Watson, who's a Cambridge researcher who broke it for the Steep project. The Systrace mechanism and
Is this the kind of semi-port of dtrace?
No, they're very
No.
different. Very, very different. Systrace was designed to create basically kind of like access control lists for syscalls that users and other processes would be allowed to call. So think of like a nice complicated, nice firewall rule set applied to a system.
Yeah, yeah.
Right? That was the design of it. It was fundamentally, I don't remember the paper, wasn't that excited about reading it, but it was fundamentally broken the concept very clearly. So it was like basically like, oh yeah, we can't.
Yeah.
All the work they did though, probably very, very valuable.
Okay, that's interesting. Thank you for that. I'll have a look, yeah. Yeah. Very cool. Yes. No. Yeah, I was actually quite surprised that there was not so much stuff out there to do these kind of things in Solaris, which is why I started to implement it. But interestingly, zones was my original kind of impetus for getting interested in Solaris. I wanted to look at zones. I've completely not looked at zones at all because I've been doing this the whole time. But eventually, I hope to get around to it. Oh, I don't think I have. No. Yeah. I couldn't say. I know that there are security mechanisms that limit the use of dtrace within certain containers, but I couldn't say. haven't actually implemented any dtrace stuff yet. So at the moment, mine is purely using ClocFS, but I hope to move on as well to implementing it around dtrace as well. But there are some existing, I mean, retrace is an existing wrapper around dtrace in Ruby, but they haven't seemed to have gone very far with it after their initial release. So hopefully I can fill the gap and also combine it with the debugging stuff. Yeah, I mean, you can find it through the LabJob site, but I mean, if I give you a code, and then you'll be able to contact me directly anyway. Yeah.
He put a couple things out there, essentially simplifying our process, what the percentage of that is going to be. We're also doing a lot of the process. What you're doing here is interesting.
Cool. Okay. Yeah, hope to hear from you. Yeah. Yeah, it rings a bell, to be honest, but I just trace is basically system call intercept on and it does not intercept with a return. It definitely can stop it from happening. It can modify it. Yeah, it might be because somebody at work actually said, oh, it'd be really cool if you could do that in Solaris kind of intercept system call because he'd just read about it. So it was probably what he was talking about, and I hadn't read it. And I said, oh, I can already do that. And that's kind of what made me write the system call process. Yeah. Yeah, that would be, yeah. There's so many directions I could go with it. I mean, as I say, I started off writing it and then I thought, hang on a minute, I can do a lot more with this now. So